Yes, thank you very much for the warm introduction. Bonjour à tout le monde. Yeah, I'll make a presentation in English, but of course you can also ask questions in French. And I would like to present some initial results of the work which I have done in my master degree, which I also did in Polytechnique Montréal with Professor Khomh and Professor Antoniol, which is about automatic generation of testing scenarios for autonomous vehicles, which are an indispensable part of a smart city, in my opinion. So here is a brief plan of my presentation. In the first place, I'll introduce the topic of self-driving cars and the known testing approaches. Then I'll present the problem of testing autonomous cars. And the limitations of the known approaches. I'll present our approach, our evaluation strategy in the results we got, and conclude and finalize the work. So possibly when thinking about autonomous vehicles, we always imagine a car with the driver inside, which is relaxing, not putting attention to the road in an ideal situation. But actually, there are 5 levels of autonomy defined by the National Highway and Traffic Safety Administration, which is an organization in the United States. And let's briefly go over them. So the 0 level is the one where we have no automation, and it's actually a typical car from the 80s. Level 1, it's when the car can control either steering or braking, but not both at the same time. And an example of this can be cruise control. And the second level is when steering and braking can be controlled at the same time, but under very particular conditions, for example, limited speed. And also the objects around the car cannot be detected in this level of automation. So if a vehicle appears in front of your car, the driver should take action immediately. An example of this can be a lane keeping assistant. The third level is when both steering and braking can be controlled and the objects around the car can be recognized. However, the driver should still pay attention. The 4th level is when it's almost complete automation, but in the certain areas and under certain conditions. And the level 5 is the full automation. Of course, we all aspire to the level 5, but the commercial vehicles we currently see can be from level 1 to level 3 at most. And in our work, we will mostly focus on the testing agents of level 2 autonomy. And let's first see what are the building blocks of the autonomous vehicles and what tasks they need to perform. So we have the vehicle with a number of sensors attached, which most commonly are cameras and lidars. They are constantly sending a stream of information, and the first goal of the vehicle is to make sense of this information, understand what are the objects surrounding it, and what is their location. Then, based on the data from different sensors and perception, the vehicle should understand where is it in the world. Then, according to its goal, it should make a safe trajectory to follow, and then using the established control policy, it should follow this trajectory. And this repeats in a loop, and this is called a closed loop behavior of the self-driving vehicle. And one of the perspective approaches today is to use so-called imitation learning, which is actually a kind of supervised learning when the driving policy is learned from the data. So the advantage is that don't need to design it manually and fine-tune to different conditions. So you learn this automatically from data, and it's a very appealing possibility. The idea is that we feed an image of the road, of the environment, and based on the decision of deep neural network, the car receives a control value for the steering wheel and for the throttle, which controls the speed. Of course, this architecture is more complicated in reality, because it's not simply enough to have one DNN. In reality, there are also some, it's combined with data from GPS, etc. But actually, the state-of-the-art approaches are still developing, and it's very modern. It's very, it's new area of research, but it's more complicated than a simple mapping from the neural network to image. But still, the biggest disadvantage is that these systems are quite difficult to explain. And if we are using such approach, even more rigorous testing should be done. And in our research work, we were focusing on designing approaches, particularly for this kind of systems. One commonly used method is to supply some test images with certain transformation to test the robustness of the classifier. And one approach is named deep test tool, where just affine transformations are applied to an image such as scaling, rotation, etc. A more sophisticated tool which produces more realistic scenarios called DPROD is using general adversarial networks to create more realistic images. And there is even a programming language which allows to flexibly define the scenarios using some commands. However, the limitation is that it just tests the perception part, or the machine learning part, and not the closed loop behavior that we discussed earlier. So actually, to test both machine learning part and the closed loop behavior, we need to have the dynamic scenarios which change in time. And before introducing the approaches for generating dynamic scenarios, I would like to present the concept of genetic algorithms, and which are very commonly used to design such scenarios. And the core idea of genetic algorithm is the survival of the fittest idea. So we have an initial population of individuals which are called chromosomes, and they're typically represented by a list of values, by a list of binary values, for example, and each value is called a gene. The second stage is to evaluate the fitness of each individual. It means how good is it to our particular goal, to our particular fitness function. Then we are selecting the best of this individual, and hopefully by combining these best individuals, we will produce even better individuals. To add some randomization and not stuck into some global minima, we also add some random changes to these individuals. And in the result, we get new candidate solutions which should be even better than the parents, and we insert them into population. We stop our search when we found the necessary quality of the individual. And one of the biggest challenges is actually the definition of this fitness function and the definition of the encoding of the chromosome, because not often you can simply encode your solution as a list of binary values. So turning to the dynamic scenario generation, there are, in the literature, there are mainly two categories of systems that are being tested. It is a lane keeping assist system where the goal is to generate such a road trajectory that forces the car to go out of the lane. And one of the known tools is asphalt tool, which represents the road as a graph of road segments and applies transformations to them, to the nodes of the graph. Another known approaches were presented in SBST 2021 tool competition, which typically represent the road as the sequence of points, which are then approximated by either some cubic splines or Bezier curves. Another group of systems is emergency braking systems, where the goal is to find a scenario where the car cannot brake in the moment that we need. And in one of the known approaches, the scenario is represented as a tuple with the fixed road shape and the changing position of the pedestrian or other vehicle, or the changing initial speed. So by looking at these approaches, some of the limitations that they have is the lack of customizability, because for example, if you represent a scenario as a sequence of points, it's difficult to add some more complexity other than the points. And if your road trajectory is fixed, you cannot test, for example, both the braking and assist system at the same time. Also, these approaches are, all of them are using full model and full simulation model to execute the scenario, which can be computationally expensive. So in our research goal was to find a way to calculate the fitness function in a more cheaper way, and also find a representation which will allow generation of different types of scenarios. And we formulated the following research questions: is comparing our implementation with the random search, and our implementation we will refer to it as AmbiGen, and also compare it to the available baselines. So actually, the generation of a testing scenario can be represented as an optimization problem. So our goal is to find a virtual environment which will be executed in a simulator, such that the car deviates, that the expected behavior in our case is the smooth driving, deviates the behavior that we observe from the simulation deviates in a big way from the expected behavior, which is a smooth driving in our case. And the second objective is the diversity of the scenarios in order to produce a big number of different case studies and explore different dangerous cases. So we propose to represent our the scenario as a sequence of environmental elements, where each environmental element will have some attributes which describe it. For example, first environmental element can be some part of the road with a description, such as the material which it has, its trajectory, its length, and the possible objects that are located on it. And now I can present how we define our second objective, which is the diversity. We basically calculate how many of the same elements there are in the two matrices. And here is the overview of our approach. First, we generate initial population of such matrices which represent the environment. Then we calculate. Then we need to transform this matrix to a test scenario, which will be a sequence of points if we consider a lane keeping assist systems, which will finally be approximated by some curve. Then we take a simplified model instead of a computationally expensive full model to evaluate the fitness. We then calculate the deviation from the expected behavior, which in our case will be deviation from the road lane center. Calculate the fitness value. We perform crossover mutation over individuals and update the population. With our representation, it's easy to perform crossover. Here is an example. We simply exchange the columns of the environmental matrices. And also see it's simple to perform mutation. We can simply change the values in the of the attributes. And here is the actual case study that we evaluated, that we used to evaluate our work. The goal is to test the lane keeping system of the car, and we need to generate valid road points, which or valid roads, and to make car follow them and not go out of the lane. And we have three attributes: the road type, its length, and the possible angle, curvature angles. Here is an example how we generate the scenario depending on the commands. For example, straight command, turning right, going straight. After going through the sequence of these commands, we obtain a sequence of points, which we then supply, which we then use to evaluate the fitness of this scenario. It means how far our model will go from the ideal trajectory. And
Dmytro, just to let you know that maybe you can conclude in 1 minute. The time is running.
Yeah, I'm concluding in 1 minute. So our approach could outperform the random search. Also, we selected one of the approaches from the state-of-the-art systems presented at SBST tool competition, which is a frenetic tool. And in a 2-hour budget, we had a similar performance, but at a 5-hour budget, our tool could find more fault revealing scenarios than the frenetic tool. And in the future, we plan to explore more complex scenarios by testing the car of the level 5 automation, for example. Yes, thank you for attention.